Okay, we've been able to describe the motion of a rotating body, and we've been able to do that by redefining variables. So we can describe this whole motion of this rotating body by thinking about a angular displacement with the angular velocity and an angular acceleration that applies to the whole wheel at once. Every part on this wheel has the same angular displacement, angular velocity, and angular acceleration. So we can have our rotational kinematic equations. What about energy, though? If I'm talking about, say, kinetic energy, then a point on the rim is going to have a different linear velocity than, say, a point more interior, and hence a point on the rim is going to have more kinetic energy than a point to the interior. So how can I deal with kinetic energy? How can I describe the kinetic energy of this whole rigid body, this whole wheel? That is a good question, and that is our next task. We want to find an analogy for rotational motion that deals with mechanical energy. So, consider this. If I were looking at just one little piece of that wheel, I would say that the kinetic energy of that ith particle of that wheel is equal to 1/2 the mass of that particle times its linear velocity squared. And that would be the kinetic energy associated with one little piece of that wheel. So the total energy of the whole wheel would be the 1/2 mv squared for every particle on that wheel. So I would say it's 1/2 the summation of every ith particle times its linear velocity squared. But we know for every ith particle that the linear velocity is equal to the angular velocity of the wheel, which is constant for every particle, times the radius to that point where that particle is from the axis of rotation. So we're going to substitute in for this linear velocity r omega, the radius to that point, times the angular velocity of the body, and then we're going to square that because it's velocity squared. Bear with me, we're headed somewhere with this. So we have 1/2 the summation of the ith mass, the distance to that ith mass squared, times the angular velocity of that ith mass squared. But the angular velocity of the ith mass is the same as the angular velocity of the wheel, because the whole wheel has the same angular velocity. So it doesn't matter whether I'm looking at the ith particle for this omega, it's the same for every particle on the wheel. So I can take that out of the summation, and I have that my total rotational kinetic energy is 1/2 times the angular velocity squared times this thing, the summation of every mass multiplied by its distance from the axis squared. Sum up all that and you get this quantity here. Well, we're going to define what we call the moment of inertia as being the summation of every mass multiplied by its distance from the axis of rotation squared, and we sum up all that for one continuous body, we get the moment of inertia. With this definition now, the rotational energy of a rotating body is 1/2 the moment of inertia times the angular velocity squared. So if I could calculate the moment of inertia of this wheel, then my kinetic energy of this rotation is 1/2 I times the angular velocity of the wheel squared. Sounds good. Note how similar this result for rotational kinetic energy is to our translational or linear kinetic energy. All we've done is we substituted in for mass our moment of inertia now, and we substituted in for velocity our angular velocity. So it has the same form as what we've had before, only one is kinetic energy for rotation, the other one is kinetic energy for linear motion. And in a sense, a moment of inertia has the same intuitive idea associated with rotational motion as inertia has for linear motion. In other words, mass measures inertia, and we described mass and inertia as being that property that resists changes in translational motion. So if you had an object that had a large moment of inertia, it would be hard to get it moving because it's going to resist changes in its motion. And once it's moving in a translational sense, it's going to be hard to stop because it's going to resist changes in its motion. So a large moment of inertia is the ability to resist changes in its motion. Same sort of thing with moment of inertia. For rotational motion, if an object has a large moment of inertia, it's going to be hard to get it moving. It's going to be hard to change its motion. And once it's already turning, it's going to be hard to stop it. So it's going to resist changes in its motion better if it has a large moment of inertia as opposed to a smaller moment of inertia. Here are some moments of inertia. It's mr squared, summation. If I just had a point mass out there, then my moment of inertia is simply m times that distance from the axis squared, mr squared. If I had 2 point masses, like a baton, revolving around an axis here, I would have an mr squared for one point mass and mr squared for the other point mass, and I would add them together, and my moment of inertia would be 2 mr squared. What happens if I had a hoop? If I have a hoop, something like this, all my mass is in the perimeter of this hoop, and it's all the same distance r away from the center. So if this hoop were rotating about its center of mass, the center of this hoop, then its moment of inertia would in fact be mr squared. In other words, it's the same as if I were just a point mass going around that circle like this, which would be mr squared. This is a hoop, all the mass is at the same radius, it's going around, it is mr squared. Sounds good. So, the moment of inertia of a point mass is indeed mr squared. What would happen, though, if we had a continuous object comprised of many point masses? It might look something like this, like a disk. Something like this, where I have a bunch of point masses all around this disk, and each mass is a different radius from the axis of rotation, the center axis. So I'm going to have a little mr squared here, larger mr squared, larger mr squared. I'm going to add up all these things together to get the moment of inertia of this disk. So I would say that the moment of inertia is a summation of all these little point masses, m sub I, times their respective radius from the axis of rotation, r sub I squared. So if I sum up all those, I will get the moment of inertia. Well, as these point masses become infinitesimally small, this summation will approach a definite integral. So we have a definite integral, r squared, dm. dm is our little infinitesimal change in mass. If we say that our infinitesimal change in mass is equal to density, which for a continuous object would be a constant, times our change in volume, because density is mass per volume, we could make that substitution into this integral, and we would have that the moment of inertia is the integral of r squared times the density dv. If density is a constant for this particular object, then I can take the constant out of the integral, and I would have that the moment of inertia is the density times the integration of r squared dv for this object. And that's how we would calculate the moment of inertia of this continuous object. Let's actually do that. Let's calculate the moment of inertia for a uniform solid cylinder of radius r, mass m, and length L. We'll calculate about its center of mass, its central mass. So if this thing were to rotate about the central mass, what would be the moment of inertia about that? We're going to consider a ring around this cylinder, and the ring has a perimeter of 2 pi r, and the thickness of the ring is going to be dr. So the area of this ring, as we go around here, is going to be 2 pi r dr. The perimeter times the thickness, dr, will give us the area of that ring. And if I give it a length, then that will give me the volume change of that little hollow cylinder represented by that ring. So I'm going to multiply by L, and that will be my change in volume. L times dA will be L 2 pi r dr. Now we're going to integrate this using the formula that we just had for the moment of inertia. So the moment of inertia of this cylinder will be the density integral r squared dv, but we'll substitute this in for dv. So we have rho, L is a constant, 2 pi is a constant. We have r cubed dr integrated from 0 to the radius of this cylinder. Well, that's not a very difficult integral. R cubed dr is simply 1/4 r to the 4th. So evaluate from 0 to the radius of the cylinder, we have density L 2 pi r to the 4th divided by 4. But we know that density is the mass per volume, and the volume of this cylinder is the cross-sectional area pi r squared times its length, its height, L. So that is pi r squared L. And if I make that substitution in the previous equation, we have this. Density of the cylinder is the density, mass over pi r squared L, times, and I'm going to factor out a pi r squared L of this other term, times 2r squared over 4. The pi r squared L's cancel out, and I end up with mr squared divided by 2. That is the moment of inertia of a solid disk, of continuous solid disk, mr squared divided by 2. So, the moment of inertia of a hoop is twice the moment of inertia of a cylinder of the same size and mass. This has twice the moment of inertia than this. Why is that? Well, all of the mass of the hoop is way out here at a radius r, so it is mr squared. Whereas the mass of the cylinder is distributed throughout the radius from 0 to r. So it's got more mass located at a smaller r to the interior of the cylinder. Hence, given as a moment of inertia, it's going to have a lesser moment of inertia than having all the mass located at a distance r away. So this has a greater moment of inertia than this. If I were a bicyclist, and say I were riding in the Tour de France, maybe what I would want if I were going long distance is I would want a wheel that looked something like this, that had a large rim and maybe not much to the interior. And what that would do is give me a large moment of inertia, and once I got up to speed, well, it'd be hard to get up to speed, first of all, because I'd have to overcome that moment of inertia. It's going to resist changes in its motion. But once I got up to speed, and I was going at a pretty good clip, then it's going to help me maintain that speed, because it's going to resist changes in its motion as far as slowing down. So once I got up to speed for a long distance, this will help me maintain that speed for a long time. So for long distance, I want this kind of wheel. But once in a while, they have a time trial where they have to go really fast over a short distance. Maybe then I might want a wheel that looks like this, because it's got a smaller moment of inertia. I don't have to overcome as much in order to gain a great speed to begin with, and hence I can access that large speed very quickly from the start, and hence for a short race, a solid wheel might actually be what I want. So sometimes you see these racers have different bikes with different wheels depending on which kind of portion of the race, the Tour de France, they happen to be doing for that stage. Here are some great moments in history. 65 million years ago, we were hit by a big rock out of the sky, ended the age of the reptiles and started the age of the mammals. That was a great moment in history for us. Then another big stone was the first wheel. We made the wheel, which allowed us to transport things from place to place. Great moment in history for humankind, because we were able to move things from place to place, made work a lot easier. Sometime later, we made a trip to that big rock in the sky, the moon, and we place a footprint there. That was a great moment in history. Some people say we never went there, but if we shoot a laser and reflect it off of the retroreflectors that were placed there by the Apollo 11 astronauts, it'll come right back to us, and that will prove that we actually were there. There are things there that could only get there because we went there. So, we went to the moon, great moment in history. Another great moment, not long after that, was the invention of the PET rock. PET rock made its inventor very rich. You sell this rock, very easy to care for, even though it had a book to help you learn how to care for your pet rock. Made sure it had enough air and other essentials for its well-being. So these were all great moments in history. Here are some other great moments in history. The hoop is a great moment in history that you should know. Its moment of inertia is mr squared. We just calculate the moment of inertia of a cylinder, a solid disk, and that is 1/2 mr squared, less than the hoop. If we were to calculate the moment of inertia of a sphere, which we could do using spherical coordinates and our moment of inertia formula, we would calculate that it was 2/5 mr squared. So by rounding off the edges, we have a moment of inertia that's a little bit less than the moment of inertia of the cylinder. It is 0.4 mr squared instead of 0.5 mr squared. A little bit less. The moment of inertia of a thin rod, about its center of mass, going like this, is 1/12 ml squared, length of the rod squared. So that is the moment of inertia of a thin rod, 1/12 ml squared. And if I were to put a thin rod on its end, like this, the moment of inertia around this axis here is 1/3 ml squared. It's greater than around the central axis, because now if I move it to the end, I'm moving more of my mass further away, and the moment of inertia goes as mr squared. So as I move more mass further away from the axis, I'm going to increase my moment of inertia. So this is 1/3 ml squared. There's an easy way to calculate this, but let me tell you that these 5 moment of inertias, these great moments in history, are moments of inertia that you should memorize, or at least put on your formula card to have easy access to. But these are 5 moments of inertia you should commit to memory. What happens if you have an object which has a moment of inertia about some central point, but then you move it away and you move the axis over here, so now this object is moving around some point like this? What's the moment of inertia of that object about some parallel axis, some distance d away from its original point? We describe this by what we call the parallel axis theorem. The moment of inertia of this object, a distance d away from an axis, so we're going around this circle like this, is equal to the moment of inertia of the object about its center of mass, which is part of that table that we just showed, plus md squared, where d is the distance that we move the axis over like this. In a sense, we can think of it this way. We have the moment of inertia about its own central mass, as it's moving like this, plus the moment of inertia of the whole thing acting like a point mass, a distance d away from the axis. So I thought of this object as a point mass moving around this axis. That would be mr squared, or md squared, where d being that distance. Plus, as it's going around, it's also turning on its own center of mass. So I have the moment of inertia about the center of mass plus an md squared. And that is the moment of inertia of the whole system as it's moving about this new point. An example would be like the Earth going around the Sun. Earth going around the Sun is a sphere, turning on its own axis. It's got a moment of inertia associated with that, but also it's got an md squared of inertia associated with it going around the sun. And that's going to be much, much greater than its own central mass moment of inertia. So there's more moment of inertia associated with it as a planet going around the sun. So the moment of inertia by the parallel axis theorem is the moment of inertia about the center of mass plus md squared. Here's an example. Consider a uniform rigid rod with a moment of inertia about its center of mass like this. We just determined a moment ago that it is 1/12 ml squared. Find the moment of inertia of the rod about an axis on the end. So if we move it a parallel distance from the middle to the end of the rod, what is the new moment of inertia? That's also on our table, so we already know what the result should be, but we want to use the parallel axis theorem to come up with this result. So we know from the parallel axis theorem that the moment of inertia about the end of the rod will be the moment of inertia about the center of mass plus md squared. D is the distance that we move our axis from the center to the end, so that's going to be equal to L divided by 2 as we move the axis down here. So our D is in fact L divided by 2. So our new moment of inertia is going to be 1/12 ml squared for the moment of inertia about the center of mass plus m times L divided by 2 squared. This is going to be 1/12 plus 1/4 ml squared. That's going to be 1/12 plus 3/12, which would be 4/12, which would be 1/3 ml squared. So the moment of inertia of a thin rod about its end is 1/3 ml squared. Let's try the same for a cylinder about its edge or a sphere about its edge. The moment of inertia of a cylinder on its edge going around like this would be 1/2 mr squared, the moment of inertia of the center of mass, plus m times the distance we move that axis squared. In this case, the distance we move the axis is from the center to the edge, which is r. So we're going to have 1/2 mr squared plus mr squared, which will be 3/2 mr squared. So a cylinder moving about its edge like this is going to be 3/2 mr squared moment of inertia about that point. If I did the same thing for a sphere on the edge, I would have 2/5 mr squared for the moment of inertia of the sphere plus an mr squared for moving the axis a distance r, and that will be 7/5 mr squared. So even a sphere on its edge will still be less than the moment of inertia of a cylinder on its edge by the fraction of 3/2 to 7/5. With this consideration, let's have a race. 3 objects of uniform density, a solid sphere, a solid cylinder, and a hollow cylinder, are placed at the top of an incline. If they are all released from rest at the same elevation, hence given the same potential energy, and roll without slipping, which reaches the bottom first and which reaches last? You should try this at home and note that the result is independent of the masses and the radii themselves. All right, so we're going to have a race between, well, I just have 2 objects here, a hoop and a cylinder. Which one is going to win going down the incline? That is a good question. I'm not sure we can demonstrate this too well with our limited camera, but I'm going to try. So, here's our incline. And here's our hoop and our cylinder. And as you look at it, maybe the cylinder looks like it's starting out a little bit ahead of the hoop. That's just from your close perspective. So they're going to start with the same potential energy. They're going to go down this incline. Which one's going to win? Well, there's 2 ways you can think about this. So we want to think about this before we do it. 2 ways you can think about this. The moment of inertia of a hoop is twice the moment of inertia, at least around the center of mass of the cylinder. So this is greater than the moment of inertia of this. Actually, we should be thinking along the edge, so it's really 2/3 as opposed to 7/5. But still, this is greater than this. So this will be harder to change its motion. It'll be harder to get this going from rest to some speed as opposed to this. This has a smaller moment of inertia. It'll gain speed quicker. Hence, based on that theory, this should make it down to the bottom before this does. Equivalently, we can think about this from an energy perspective. If I start with an mgh for both of these, being that they're the same mass, and I'm going to end up with a kinetic energy of both of them being the same at the bottom because the energy will be conserved. If they both have the same kinetic energy at the bottom, and this one is a greater moment of inertia, and the kinetic energy is 1/2 I omega squared, then if this has a greater moment of inertia I, then it will have a lesser angular velocity omega. So this will have a greater angular velocity with the same kinetic energy, hence it'll be spinning faster and moving faster. So again, from that perspective, this should win the race. I'm not sure this is going to work too well for this very short race as we see here, but we'll try it. All right, hopefully you saw that the cylinder beat the hoop. So we'll go with that. So it would look like this. The cylinder beats the hoop, and if we had a sphere to race as well, that would make it to the bottom before the cylinder. So it goes in ratio of the least moment of inertia to the greatest moment of inertia. Actually, if we were to combine rotational and translational motion, we would get rolling motion. If I think about this disk right here, as this rotating about its center of mass, the linear velocity of a point on the top is equal to the angular velocity, omega, times the radius to that point. And it's equal to some velocity moving in this direction, which would actually be the velocity of the center of mass. Now, a point on the bottom, as this is rotating, is going in the same velocity but in the opposite direction as we're going in the bottom as this is rotating in this direction. So the top point has a velocity this way. The bottom point has the same magnitude velocity going in the opposite direction. That's for rotational motion. If I had translational motion, this whole object is moving this way, and every point is translating at the same speed v to the, as you're looking at to your right. So if I were to combine these two motions, rotating motion plus the whole object translating, I would get rolling motion, where this thing is rolling along like this. So combining these two motions, I would get this. The top of this disk is actually moving at twice the velocity of the center of mass, while the bottom of this disk is momentarily stationary because it's got two velocities, a negative v this way and a v this way, and they're canceling out. So my velocity at the bottom of this disk is actually momentarily 0. How about that? That is true for any rolling motion like this, and you can think of it as this combined motion of rotating plus translating, or you can think of it as just one rotation about this pivot point. This rolling motion is pivoting about this point here. That pivot point is 0 at that moment, but the top of this wheel is going through this whole arc like this, so it's going through the greatest amount of distance, and hence it's actually moving at 2v as opposed to the middle of the wheel, which is moving at just v. So the top of the wheel is 2v, v, 0. If you ever try to take a picture of a bicycle moving along using old style film, you would find that the top of the wheel is kind of blurred while the bottom of the wheel is fully in focus, because the bottom of the wheel is momentarily stationary and the top of the wheel is going at twice the speed of the bicyclist. The actual movement of a point on the rim of this wheel would actually look like a cycloid. So as the point is moving, it reaches twice the velocity at the top of the cycloid, and then as that point reaches the ground, it momentarily stops as it becomes the pivot point, and then it goes through the cycloid again. Picks up speed to twice the velocity of the wheel itself, and then momentarily stops at the bottom. A while ago, I actually constructed this MathCAD program to illustrate this. Watch this wheel as it's moving at constant turning to the right. And as we graph the motion of a point on its rim, it goes through this cycloid where it momentarily stops at the bottom. It stops, reaches twice the velocity at the top of the wheel, and then stops. This took me a while to program this, or you're going to have to watch it 3 times. Get my money's worth out of it. Okay. Let me tell you a quick story, hopefully. Years ago, I used to work for the longbow missile simulation associated with the Apache helicopter. Apache helicopter can shoot 16 missiles, and a lot of times they're Hellfire laser-guided missiles, but they also can shoot a longbow Hellfire missile, which is radar-guided, and fire and forget. So you shoot it, and you fire, you pick a target, and you forget, and you hit the target. All right, so you're dealing with this system, and the way it works in the battlefield is you have a bunch of helicopters, Apache helicopters, and above some of the helicopters, they have a big fire-controlled radar above the rotors. And this ellipsoid-looking thing above the rotors is the radar. So if you had your helicopters bunkered down behind a hill, you could raise up and just show the ellipsoid radar and take a fire-controlled radar scan of the whole battlefield, get data on all the combatants in the battlefield, so what the tanks are doing in the battlefield, where they're going, how fast they're going, what direction they're going, and get that scan of the whole battlefield. And you just kind of go back down. And one thing you might do is, if you had this longbow missile, is you could shoot the missile. It would go in the air, and you haven't even told it what to hit yet. So it's in the air already, and you look over this radar scan of the battlefield, and you look at all the tanks out there, and you say, I want to hit that one. So you quickly tell the missile, hit this guy over here, and the missile is already in the air, will then turn on its radar and look in that area and try to find the guy that you told it to hit. And once it found that guy, it'll lock on to him, and then whatever he does then will be inconsequential because he's already locked on, and the missile should hit that guy. Well, each of these missiles have their own radar system. So, once you're locked on, you're in trouble, because it doesn't matter if you try to combat that missile unless you can shoot that missile down in midair, which is pretty hard. You're stuck. It has its own radar system. Each missile costs, at least at the time that I was working on this years ago, costs $750,000. So if you shoot one of these missiles, you have spent $750,000. Apache helicopter has 16 of these things. So that's why you do simulation. You want to do a simulation of the missiles, which have the same software as the actual mechanical system, so that you can shoot as many missiles as you wish in simulation and not spend all that money. And so in the simulation, you work on it, you play games, and you try different scenarios and different things. Can't tell you too much because some of it's secret, but I'm just telling you what you probably can find on the internet. But you would shoot a bunch of these things, try to optimize the parameters, and then when you finally think that you've got it all figured out, then you have to actually test it on the mechanical system. The mechanical system will have the same software as what you've been using in the simulation. So you go down to Eglin Air Force Base and you set up an Apache helicopter, and you have a Russian T-80 tank going around the track, and you actually shoot one of these $750,000 missiles. And the first 7 times you do this, the missile hits the tank, dead aim, blows up the tank, get another tank. So successful the first 7 times you test it out. However, on the 8th time, tank's going down the road, and you shoot the missile and totally misses, not even anywhere in the ballpark. And so the general kind of turns to you and says, all right, what happened? And you go, I don't know. I'll give you the answer next week. So you got to figure out why the simulation and why the missile missed. That is a very good question. Well, I wouldn't be telling you this story unless it had something to do with what we've been working on here. Now, we know that if you fire and forget, and if you wait some time before you tell the missile which target to hit, there's been a delay of time. And in that delay of time, the tank can decide to move somewhere, and it's moving at a particular velocity, at a particular orientation. So involved in this trying to hit the target is a computer calculation as to where that target should be when the missile receives that information. So the missile will look in that area and have some kind of footprint to look in that area, and if it sees the target, it'll lock on and then hit the target. The problem is it's based on the velocity of the tank, and maybe that velocity might not be picked up correctly. Maybe if you took your radar scan of the battlefield, you're taking a radar scan of the top of the wheel, the top of the tread of the tank, as opposed to the tank itself. Maybe on the first 7 tries, you actually got more of the tank than the tread, and you actually got the true speed of the vehicle. That was put in the algorithm, and you actually hit the target. While on the 8th try, you actually got more of the tread than the tank, and actually that's moving at twice the speed of the vehicle. And the algorithm actually predicts that the vehicle is somewhere where it actually is not. So your missile goes to that somewhere where it's not, doesn't find anything, totally misses the target. So how do you deal with that? Well, you get on the phone, you call up all of your enemies, and you say, could you please put skirts over all of your treads on your tanks so that we don't have this problem? And they say, sure, anything for you. We'll do it. We're happy to do that. And so that's the answer to that problem. Actually, I can't really tell you the answer to that problem. You can probably maybe figure it out. That actually might be secret, but that is something that deals with just the physics. So we have the physics of a wheel. Top of the wheel is moving at twice the velocity of the vehicle itself, and it comes into play into everything that we do. So that's our second short lecture in Chapter 10.